Okay, boys and girls, welcome to the second part of the video for today. And in this video, we're going to look at optimization. So we're going to concentrate today on optimization, and we're going to use optimization to solve real life problems. That is our goal for today, to use optimization to solve real life problems. Let's get started. So what is optimization? It is a method to find the greatest amount of building supplies or resources to maximize a situation. If you're going into engineering, you probably will. I had to take a class called engineering math, and in engineering math, we do things like this. We look at, I'm sorry, not engineering math, but business engineering. And in business engineering, we look at things like maximizing, minimizing functions for better procedures. It's also used in business and medicine. If you go into business, you probably have to take a business calculus, and this is where we would do things like this. Okay, here's some steps. It's just like a related rates. The steps seems like there's a lot, but it really isn't. We want to understand the problem, read the problem carefully, ask yourself what are your knowns, what are the given quantities, what are the given conditions. It's always helpful to draw a diagram. You want to introduce variables that make sense, just like we did with related rates. In this one, we're going to create what we call a primary equation, and there's sometimes we're going to need a secondary equation. Okay? Then we're going to reduce, using the secondary equation, we're going to reduce the primary equation to have one single independent variable. We're going to determine the feasible domain, and then we're going to solve. Somewhere in there, we're going to use derivatives because, after all, this is application of derivatives. So let's just start with the problem. We want to find two non-negative numbers whose sum is 9, so that the product of one number and the square of the other number is a maximum. Okay, so we want two non-negative numbers whose sum is 9. So let's write our first equation. Our first equation would be x plus 9. I'm sorry, x plus y equals 9. Two non-negative numbers whose sum is 9. The product, so that means multiplication of one number and the square of the other number is a maximum. So what are we trying to maximize? We have the product of one, the square of the other, and we want that to be a maximum. I'm just calling it z, so when we take the derivative, we'll have something to call it. This is my primary equation. It's my primary equation because this is what I'm trying to optimize, primary equation. This is my secondary equation. I'm going to use my secondary equation to eliminate a variable in the primary equation. Okay, my primary equation, this is what I'm trying to maximize. This, and to maximize it, I have to take the derivative of it. But I don't want to use implicit differentiation, so I'm going to have to get rid of one of the variables. Which variable would you like to get rid of? It doesn't matter, but it seems to me it would be easier to write this as to get rid of the x. So we can say that x is equal to 9 minus y. Then I can substitute into the second equation 9 minus y times y squared, and it's equal to some value z that we're trying to maximize. Okay, so this is the equation I can easily find the derivative of. So z is equal to 9y squared minus y cubed. I'm taking the derivative with respect to y because I don't want to use implicit. So when I take the derivative, I get 18y minus 3y cubed squared. Okay? I want to maximize this. So anytime I want to maximize it, what I want to do, I want to set it equal to 0. So I'm going to factor factor out of 3y, and I get 6 minus 3. If I factor out of 3, I get 6 minus y equals 0. So I get y equals 0, y equals 6. Which of those will be a maximum number? Which of those would be maximum? Okay, so how do we determine that? Well, let's take the second derivative. Let's use the second derivative test. Okay, so if I take the second derivative test, I get z double prime would equal to 18 minus 6y. Then I can evaluate z of 0, and I get 18. I can evaluate z of 6, and I get 18 minus 36. I don't really care what that number is. I just need to know that it's negative. Okay? So because z of 0 is positive, that means that it's concave up, and that's going to be a minimum. But z of 6 is concave down, and that's going to be a maximum. So if I want, it says find two non-negative numbers. So what I found is that y is equal to 6. Then what is x equal to? Then x, going back to my secondary equation, x is equal to 3. So those two numbers, when I add them together, I get 9. And then the maximum value they will be is, that z would be 3 times 36. They didn't ask me that, but if that is the maximum that I could get from two numbers that add to 9 and whose product xy squared, the maximum that could be is 36 times 3. Okay, does that make sense? So you see what we did? We found the secondary equation, we found a primary equation, we brought it all down to one equation, and this is where the second derivative test is a really sweet test because I didn't have to take a sign chart. This is another popular problem that you will run up against. So we have a rectangular pen, and within that rectangular pen, we want 3 parallel partitions, and we know that it's going to use a total of 500 feet of fencing. So what dimensions will maximize the total area of the pen? So what we need to find is our primary equation. So because we're trying to minimize an area, we need an area formula. So our primary equation, what would be the area of this pen? The area of this pen is simply x times y. Okay? So that's my primary equation. I need a secondary equation. What other information are we given? Well, we're given that we use a total of 500 feet. So that's kind of the perimeter. So what would be the perimeter? So my secondary equation, the perimeter, I have 1, 2, 3, 4, 5 x's and 2 y's. And together, that has to equal to 500. So I have my primary equation, I have my secondary equation, and with my secondary equation, I can eliminate a variable. Let's eliminate, I don't know, which one you want to eliminate? Y? I'm sorry, we're going to eliminate x, so we're going to solve for y. So y is equal to 500 minus 5x over 2. So now, let's look at this. This is what we're going to minimize. So our area formula is x, and then y is 250 minus 5/2 x. Again, I'm going to distribute this because I don't want to use the product rule to multiply. So I get 250x minus 5 over 2 x squared. Okay, so now I'm going to take the derivative of a with respect to x. So I don't have to use implicit. I get 250 minus 5x. Oh, that's not too bad. Is that right? 10 over 5x. Yep, That's not too bad, is it? So I'm going to set that equal to 0. And I get 5x is equal to 250. So x is equal to 50. Okay. Did I answer the question? What dimensions? So I have x, I need y. So how would I find y? Well, I know from here that y is, oh, first of all, I have to determine if that's a max or a min. So we forgot a step there. I have to use the second derivative to determine if that's a max or a min. And so a double prime, that's going to be an easy fix because a double prime is equal to -5. So that means that the second derivative, the function is always concave down. So therefore, this has to be a maximum. Okay? So we know that's the maximum. So now we find y is equal to 500 minus 250 over 2. That was probably not the easiest way of doing that. Excuse me. So 500 minus 250 is 250. 250 divided by 2 is 175. So my dimensions are 50 by 175, if my math is correct. Okay? No, 125, sorry. 125. Okay? All righty, boys and girls, let's look at the next problem. Okay, this is another popular problem that you will run into. In this problem, we have an open rectangular box, which means there's no top on the box. It has a square base, and I've noted that by both of these are x's. And it's made of 48 square feet. And we want to know what dimensions will result in a box with the largest possible volume. Well, the first thing we have to do is write the equation for the volume. So the volume of this box, because that's going to be our primary equation, the volume is going to equal to x squared y, because the volume is length times width times height. And since my bases are the same, that's my primary equation. All right, what about my secondary equation? What piece of information can I use to write my secondary equation? How about the fact that this is 48 square feet? That is the surface area of that box. So let's write a formula for the surface area. So we know that the surface area is equal to 48. So surface area would be the sum of all the faces, the areas of each face. So this face has an area of x times y. And I have 4 of those. So this has the same area. So there's 1, 2, 3, 4 that have that area. So this will be 4xy. The area of the bottom is x squared. And there is no top. If it had been closed, then it would be 2x squared, but since there's no top, we don't write that. All right, I know my handwriting on this is really bad, but can make it a little bit better. 4xy plus x squared. Okay? So now I have to eliminate a variable. Oh, let's eliminate x. Let's solve for y. So y will equal to 48 minus x squared over 4x. That doesn't look pleasant, but I think it's going to clean itself up. So let's replace the y in our primary equation, because that's where we have to find the derivative of that. So this is going to be x squared times 48 minus x squared over 4x. So this x and this x will cancel. So this is going to give me v is equal to x times 48 minus x squared over 4, which would give me 48 divided by 4 is 12. So that's going to give me 12x minus 1/4 x cubed. Alrighty, let's take the derivative. Let's see where this leads us. Let's take the derivative. So that's 12 minus 3/4 x squared equal to 0. So x squared is equal to minus 12 divided by 4. I'm sorry, multiplied by 4, which is 48 divided by 3. 16. Check my math, please, which makes x equal to plus or minus 4. Now, we don't deal with the negative 4 because x is a length, so negative 4 is outside of our domain. So we get x is equal to 4. Well, let's see if that is going to give us our, if the second derivative would make that positive, and we could pretty much see that it would if it makes it a maximum, because the second derivative is going to equal to negative 6 over 4x. So it means that when I put in 4, I get a negative answer, so that's a maximum. So my answer is x equals 4, but that's not my only answer because now I have to find y, and y is equal to 48 minus 16 over 16, which is 48 minus 16. It's a shame, but I really don't know that answer. 232. So y is equal to 2. So my dimensions for this are going to be 2 by 4 by 4. Because x is 4 and y is 2. So 2 by 4 by 4. Okie dokie, boys and girls. Okay, last one, boys and girls. Let's do this. This is probably the most difficult one that we're going to do today. And tomorrow we're going to delve into some that are slightly more, yeah, they're hard. Okay, so let's look at this one. And this one, again, it's going to be the most difficult one we do today, but it's okay. So we want to find the point on the graph of the function y equals x squared that's closest to the point 2.5. So y equals x squared looks like this. And we have a point x equals 2, y equals 1/2. We're just going to say it's here somewhere. Oh, it'll be down here somewhere. It says outside that parabola. I don't know where it is on that parabola. Let's just put a spot. Okay. And I want to know the shortest distance from here. So there's several different ways I could get to this parabola from that point. And I want to know the shortest. Which one is the closest? Okay. So what we're going to have to use is the distance formula. Okay, so do you remember that the distance formula is equal to x2 minus x1 squared plus y2 minus y1 squared. Do you remember that distance formula? That looks so pretty right now. All right, so we have an x value and a y value. So we're trying to find out, we have an x, we can call this x2, we can call this y1, but then we have x1 and y1. So how do we get around that? Well, I know y equals x squared. So I can replace the y with x squared. Okay? So this is x1, or we can call it x2. So I'm going to call this x2, this is y2. So my formula now looks like this. D is equal to x2, we're going to say is 2 minus x, quantity squared, plus y2 would be 1/2 minus y1 is going to be x squared because y is equal to x squared. So I'm just replacing it with x squared, so I'll have all one equation. So in other words, this became my secondary equation, and this is my primary equation because this is what I'm optimizing. Okay, now to take the derivative of that is going to be a pain in the butt. So let's not take the derivative of that. What we know, if I ask you which one was bigger, the square root of 29 or the square root of 27, you wouldn't actually have to find the actual square root to tell me which one's bigger. You could automatically say, okay, because the 29 is bigger than 27, the square root of 29 is bigger. So we're going to use that thought to just ignore the square root symbol. Because if I make this as big as possible, if I make what's inside this radical as big as possible, then I am maximizing that distance. Okay? So I am just going to ignore the radical and just maximize what's inside of that. So 2 minus x squared plus 1/2 minus x squared, quantity squared. If I maximize this, then I maximize what's inside that. I've maximized the radical. Okay? So I'm just going to take the derivative. So taking the derivative with respect to x would give me negative 2 minus x, and it's negative 2 because of chain rule, because I have to take the derivative of that negative x, plus, again, take the derivative of the inner function, which would be negative 2x, times the derivative of that outer function, which would be 1/2 minus x squared, and then that 2 dropped, so times 2. Cleaning that up, I get negative 4 plus 2x minus, let's see, that's negative 4x times 1/2, which would be 2x, and then plus 4x squared. 2x times 2 times x squared. And they're both negative, that's why it's a plus. So the 2 x's zero each other out. Oh, that's not so bad. I get 4x squared minus 1. So setting my derivative equal to 0, I get x is equal to plus or minus 1. That's not too bad. So which one is a maximum? Well, again, my second derivative ended up being 4x squared minus 1. So if I take my second derivative, d double prime would give me 8x. So we see when it's negative 1, that's going to be negative x. When it's positive 1, it's going to be positive 8. So we're trying to find the closest, so we're trying to find a minimum. This is concave down, so that produces a maximum. Concave up, this produces a minimum. So my answer is find the point on the graph. So it would be x equals 1, and then putting 1 back into y, y equals 1. So the point that's closest to the point 2, 1 would be at 1, 1. Okay? All right, that's the last one for today. Your exit ticket is going to be 2 quizzes, and they're both listed in Google Classroom. Have fun.